Now let us see what formality is. See, in general, when we speak of ionic compounds, see, because ionic compounds consist of ions, right? Now, when they consist of ions, unlike the covalent compounds, which consist of molecules, now when there are molecules, it is proper to say molecular weight. Okay. And in case of ionic compounds where you don't have molecules, rather you have oppositely charged ions, it is not proper to say molecular weight. It is proper to say formula weight or, of course, ionic weight. Okay. No much difference. Calculation is, of course, the same. There is just a small theoretical difference. Now, just like we use the word molecular weight in case of covalent compounds, we use the word formula weight in case of ionic compounds. Similarly, the concentration of the solutions of these covalent compounds is expressed in terms of molarity. In a similar way, concentration of the solutions of ionic compounds is expressed in terms of formality. So, in simple terms, molecules, molecular weight, molarity in case of covalent compounds. Similarly, ions of formula weight, formality in case of ionic compounds. Right. So there is no much difference between molarity and formality. But the thing is used in case of different compounds. That's it. Let me tell you that formality is the number of formula weights or gram formula weights of the solute present in 1 liter of the solution at a given temperature, since it depends on temperature. So this is the definition represented by F, number of gram formula weight of the solute by volume of the solution in liter. Now, what is number of gram formula weights, or how do we calculate the number of gram formula weights? See, this can of course be given as weight by gram formula weight. Okay. So the overall thing can be written as formality is equal to weight of the solute by gram formula weight of solute into straight away 1000 by volume of solution in ml. 1 by volume of the solution in liter or 1000 by volume of the solution in ml. That's it. Coming to units, just like in case of molarity, it is mole per liter. In this case, it can be given as gram formula weight per liter. Now, coming to effect of temperature, again the same. See, when temperature is increased, volume of solution increases. As volume and formality are inversely proportional, formality decreases. Okay. So that is about the effect of temperature on formality. Now the next method of expressing concentration, that is normality. A small difference. Normality can be given as number of gram equivalents, just like gram moles in molarity, gram formula weights in formality. Here it is gram equivalents or equivalents of solute present in 1 liter of solution at a given temperature. Okay. This can be mathematically given as normality is represented by capital N, then number of gram equivalents of solute by volume of solution in liters. Okay. Now, what is number of gram equivalents of the solute? How do we calculate that? So this is nothing but weight by gram equivalent weight, right? So this can be modified as weight of a solute by gram equivalent weight of solute into 1 by volume of solution in liters. Or else the same thing can be modified as the same thing multiplied by 1000 by volume of solution in ml, right? So this way normality can be calculated. The most important one, of course, is this, most frequently used. Next. See, normality can also be calculated taking number of milli-equivalents into consideration. But when you take milli-equivalents, remember, take volume of the solution in ml. Okay. Now different conditions, as we have seen in case of molarity. See, when strength of solution is given in gram per liter, normality can be calculated using this. Strength of the solution in gram per liter by, see, strength has already covered the weight of the solute and volume of the solution. So the thing that we are left with is gram equivalent weight of the solute. That's it. Now, see, when percentage strength of the solution is given in weight by volume, normality can be calculated using this formula. Percentage strength of the solution, remember, it has to be in weight by volume, into 10 by the gram equivalent weight of the solution. Okay. Now, when percentage strength of the solution is given in weight by weight, to convert the weight of the solution into volume, you need density as usual. In this case, normality can be calculated as percentage strength of the solution, very important, to be taken in weight by weight, into density or specific gravity into 10 by the gram equivalent weight of the solution. Okay. Then, see, when volume strength of hydrogen peroxide is given, normality can be calculated using the formula volume strength is equal to, volume strength of hydrogen peroxide is equal to normality multiplied by 5.6, or else go with this. 10 volumes is equal to 1.786 normal. Okay. Coming to units, it's equivalents per liter. Just like in case of molarity, it is moles per liter. In this case, it is equivalents per liter. Then coming to effect of temperature. See, when temperature is increased, obviously volume of the solution increases. When volume of the solution increases, as volume and normality are inversely proportional, normality of the solution decreases. That means when temperature is increased, normality of the solution decreases. Now, different types of solutions on the basis of their normality. Normality are 1n solution. We know that normality is equal to number of equivalents or gram equivalents by volume in liters. Anyway, this is 1 liter as per the definition. And this we want it to be 1. Then what this has to be? It has to be 1 equivalent, right? So 1 equivalent of a solute is in 1 liter of a solution. Then that is what we call normal or 1n solution, right? Similarly, the other things. Decinormal or 0.1 n solution. 0.1 equivalent of the solute is in 1 liter of the solution. That is what the decinormal solution is. This is about normality. Now let us go for the relation between molarity and normality. Okay. Now, see, molarity is weight of a solute by gram molecular weight of the solute into 1000 by volume of the solution in ml, right? Coming to normality. Yes. It can be given as weight by gram equivalent weight of the solute into 1000 by volume of the solution in ml, right? Now, take the ratio. everything gets cancelled except the molecular weight and equivalent weight, right? So now this can be given as molarity by normality is equal to gram equivalent weight by gram molecular weight, right? Or can be given as normality into gram equivalent weight is equal to molarity multiplied by gram molecular weight. Okay, very important. Now let me give you an example on this. Let us consider say a regular one, sulfuric acid. You know, the gram molecular weight of sulfuric acid is 98 grams. And when it comes to gram equivalent weight, it's 98 by 2. Now this 2 is its basicity, right? The number of replaceable hydrogen atoms. Now this is 49 grams. Now let us use the formula normality into equivalent weight is equal to molarity multiplied by molecular weight, I mean gram molecular weight. Now in this case, it can be given as a normality is equal to molarity multiplied by 2. Now this 2, of course, is a basicity, right? So in case of acids like sulfuric acid, any acid, it can be given as a normality is equal to molarity multiplied by basicity, right? And in case of bases, it can be given as normality is equal to molarity multiplied by acidity. We know what acidity is. The number of replaceable hydroxyl groups present in one molecule of the base. Say in case of salts, normality can be given as molarity multiplied by total positive charge or negative charge. And in case of oxidants or reductants, normality can be given as molarity multiplied by change in oxidation state, right? So that is all about the relation between normality and molarity. Overall, in general, it can be given as normality is equal to molarity multiplied by, see these all, that is basicity, acidity, charges, change in oxidation state, is in general given as n factor. Okay, you know what n factor is and how to calculate n factor, right? So that is the relation between molarity and normality. Now let us take some relations used in volumetric analysis. Generally during titration. The first one is dilution law. In this, the first one is for molar solution. Now, even in this also we have two cases. The first one is M1V1 is equal to M2V2. Say this relation is actually used for calculating the molarity of the resultant solution formed on diluting the given solution or the standard solution or the solution of which concentration is known already. Let me give you some clarity. For calculating the molarity of solution formed on dilution, look at the things. Now these two are the molarity and volume before dilution. And these two are the molarity and volume after dilution. Right? Suppose we got a 0.1 m solution whose volume is 100 ml. Just an example. We got 100 ml of 0.1 m solution to which 900 ml of water is added. We have just diluted it. What is the molarity of the resulting solution? M2 is what we have to find. And the final volume is 100 plus 900. Right. So we will be calculating the molarity of the solution formed after dilution. This can be calculated. Right. So this is in fact the first case. We can calculate the molarity of the resultant solution. Now, let us take something related to the same. You know, the volume of water to be added can be calculated. Let me tell you that. Again, go for M1V1 is equal to M2V2. Now, in this case, anyway, these are before dilution, M1 and V1, M2 and V2 are after dilution, right? Now, in this case, volume of water to be added can be given as final volume minus initial volume. Let us take the same old example. We got 100 ml of 0.1 m solution with us. And suppose if we want to make it 0.05, what volume of water has to be added? Calculate V2. Now V2 is 200. That is the total final volume. Therefore, volume of water to be added can be given as V2 minus V1. Nothing but this. Okay. So even this can be calculated. See, for volume of water to be added, we can also use a direct relation. Of course, merging these two or mixing up these two, we can give a relation M1 minus M2 by M2 into V1. Supposing if that is used in this case, see, M1 is 0.1, M2 is 0.05 by again M2 0.05 into V1 is 100. Simple. We got 100 ml. So this way we can use dilution law for molar solution for two things. First one, for calculating the molarity of the solution obtained on dilution. The second one is a volume of water to be added. This can be calculated when a solution having known concentration, I mean a standard solution, is used to get a solution of required concentration, just like what we have seen here.